Right, guys, we are going to do our last podcast for sort of our intro stuff before we hop into the real fun and excitement of environmental science. And so we're going to talk a little bit today about energy. This is sort of part of the chemistry / physics recap stuff. So first off, what is energy? Energy is defined as the ability to do work or to transfer heat. Usually in most science classes, we're going to use the joule, okay, as our main unit. But you're going to see energy in a lot of different ways as well. So you can see energy as calories, as kilocalories. Now, if you'll notice here, one of the big differences is when we talk about food and food calories actually aren't regular calories. They are kilocalories. And you can tell the difference because regular calories are lowercase and food calories are uppercase. And you're like, that seems like a pretty small difference. And it is. Just remember that every food calorie is actually 1,000 regular calories, okay, that we would normally use for energy inputs. You'll need to know these conversions, okay, so you can just sort of start plugging those into your brain, making sure that you know those. Sometimes we'll talk about things in terms of British thermal units, and so 1 BTU is about 1,000 joules, okay, rough estimation. Obviously it's actually, okay, 1,055 joules, but you know, you can make a really rough estimate that a BTU is pretty close to a kilojoule. And then kilowatt hours. Now, kilowatt is actually a measure of power, not of energy, strictly speaking. But if we convert that into kilowatt hours, then we can equate that actually to joules. And what you'll notice here is that that is a ginormous number. Okay, so 1 kilowatt hour is about 3.6 million joules, which is a pretty big amount. Okay, so where does most of our energy come from? Most of our energy on the Earth is going to come from the sun. Now, how exactly does that work, really? Well, remember that, so energy from the sun comes in, it's going to heat the planet up, okay? So we get heat energy from the sun, okay? We get light, okay, that goes to plants. Plants take that light, okay? And what do the plants do with it? The plants convert it into food or chemical energy. Okay? And then how does that work for us? Well, that works in multiple ways. So those plants then can get converted into fossil fuels over millions of years. Okay? We could actually take the food stuff from the plants and convert it into energy for animals. We can convert that food directly into energy in ways like ethanol. Depending on the type of plants, we could just burn the plants. Okay? And so pretty much any energy on the Earth comes from the sun in one way or another. And you might be thinking in your head, you're like, okay, well, I accept all of that, but what about things like wind energy? Okay? Well, do you ever stop to think about where wind comes from? Wind actually comes from pressure differentials, which is the result of uneven heating of the Earth. And so the Earth gets heated up in different ways in different places. That changes the pressure. You get a pressure gradient. That's where wind comes from. So ultimately, wind energy also comes from the sun. So lots of different forms of energy come from the sun. Not all. Okay, so something like nuclear energy, say, doesn't come from the sun. Tidal energies, we can make the argument that it kind of does because of gravitational pulls, but tidal energies are largely due to the gravitational pull of the moon on the Earth, on the oceans of the Earth, and so that you can say probably doesn't, but in most cases, most energy that we have comes from the sun. That energy from the sun comes in the form of electromagnetic radiation, okay? So this is a nice little picture of electromagnetic spectrum. If you're looking over here, this is the visible spectrum. That's the stuff that we can actually see. Most of the energy from the sun kind of comes in a little narrow band of electromagnetic radiation. That's most of what we get, some from UV and from infrared through visible. But we also get some of the others, okay? And then down here we've got things, we've also got cell phones and stuff like that that fall in the spectrum. So your cell phone signal, the Wi-Fi signal that you're probably watching this video on right now, microwaves, radio signals, gamma rays, X-rays, visible light, they're all electromagnetic radiation. Hopefully you know that from your other science classes. Electromagnetic radiation travels in the form of photons. If you remember, you sort of got the dual nature of photons, that they act like waves. In some cases, they act like particles in other cases. We're not going to get into all that. That's sort of a physics, chemistry thing. But just know that photons are how it gets there. Electromagnetic radiation is the way that the sun gets its energy to us. So some forms of energy that we need to talk about. So potential energy is in general any energy that's stored but that's not released. So we tend to think about it like we learned it in middle school that potential energy was like how high up something was, and that if it fell, it was converted into kinetic energy. And that's partially true, but potential energy means essentially what potential sounds like, that it's energy that is stored that isn't being used really or isn't being released yet. And so that would also then include chemical energy, okay? So chemical energy is potential energy that's stored up in the chemical bonds. And so when those bonds are broken in a chemical reaction and something forms into a different sort of molecule, then that releases some of that bond energy. Now some of it obviously is consumed in making the new things, but a lot of it is released in that point. So that's why like fossil fuels and stuff like that are so valuable. Kinetic energy is energy of motion. And so what we've got here in this diagram, this is a diagram of a dam, obviously, a hydroelectric dam. And so in the back part of it, okay, the part that we can't really see, there's potential energy from all the water that's basically stored up there. And then as that water starts to flow down through the dam, then that becomes kinetic energy. And of course, we're going to try to harness that and then convert it into electricity. Okay, so kinetic, whenever you see the word kinetic, just think about motion. We're going to use kinetics a lot in a lot of science classes. Temperature is the average kinetic energy of the particles of the substance. Okay, so when we measure temperature, what we're essentially measuring is how fast are all of the molecules or all of the atoms moving around in that substance. Okay, and so if we've got a really low temperature, the speed of the particle slows down a lot. It never actually completely stops, but it will definitely slow down. If they're moving really quickly, like in a gas or something like that, then it's got a much higher temperature. And the more we heat up the temperature, what we're actually doing at the atomic level, or at the molecular level, is that we're making the particles move faster and faster and faster. And so the reason they change from, say, solid to liquid to gas phase is because they're getting more and more energy, and so they can move around, and so they can separate from each other. And so in solid phase, they're packed together, liquid a little less so, and then in gas phase, they actually escape and can kind of break free of each other. So let's talk real briefly here about a couple of laws of thermodynamics. Hopefully you remember these again from your physics classes. And if you haven't had physics, that's okay, because you probably talked about these things in middle school. You just didn't talk about them in maybe the same terminology. So first law of thermodynamics, energy is neither created or destroyed. You probably called this the law of conservation of energy before, and that will work. But technically this is the first law of thermodynamics. It means that energy is conserved. Okay, that we can convert it into different forms. Okay, whoops, I didn't mean to gloss through that. We can convert it into different forms, but that we can't actually destroy it. A little bit. So that we can take potential energy, convert it into kinetic energy. It's all going to be converted. Some of it's going to be converted into heat energy. Okay, but it's not ever going to go anywhere. It's all getting converted into different forms of energy. Now, it might not be usable energy. We're going to talk about that in a second. So when you go up in the roller coaster, you've got really good potential energy. Okay, up at the top, you start to come down. That's being converted into kinetic energy. You can never go back up to the top part of the hill, right? Okay, all of the hills are smaller unless they actually grab you with the chain and pull you back up. So why is that? Well, because some of the energy is lost to heat energy. It doesn't mean that it's destroyed. It just means that it's converted into a non-usable form at that moment. So, second law of thermodynamics goes right along with this. When energy is transformed, the amount of energy stays the same, but the ability to do work diminishes. Now, why is that? Well, if we go back to our very initial definition of energy here, okay, it says that it's the ability to do work or the ability to transfer heat. And so the transferring of heat, that energy becomes much less usable then. Okay, it's not usable in any real good form for us. And so the second law of thermodynamics says that things tend to go to an area where we can't use all of the energy anymore. This goes into the idea of entropy. Entropy is basically the randomness of a system. You might have heard of entropy described as the disorganization of a system. Entropy is one of those science terms that we can discuss on a real simple level like disorder or randomness, but it's really a lot more complicated than that. There's a lot of math that goes into what entropy actually is. You're pretty safe to assume in most of our situations that it's randomness or disorder. Okay? What it really means is things that are less usable for us in terms of energy. This is why if you've ever heard the term heat death of the universe, all of the energy that we have is in a certain amount of usefulness, and as we use it, second law of thermodynamics says that it becomes less useful, and so therefore eventually all the energy in the universe, it's hypothesized anyway, is going to turn into heat energy. So this leads us to a couple of terms that are pretty important for us. Energy efficiency is basically the ratio of the work that's done compared to the total amount of energy that went in. And so if I said, okay, well, I put in, the work that was done was basically 8 parts of the 10 that I put in, and so that would mean that we were basically 80% efficient in that case. So I put in 10,000 joules of energy, but only 9,000 of them actually got used, then that would be 90% efficient. Okay, so that's just a ratio. Energy quality is a pretty cool term because what energy quality means for us is that it's how easy it is to use the energy for work. Okay, in other words, how much of it gets wasted in using it. So let's just real briefly sort of talk about a couple of things. So let's talk about wood compared to, say, gasoline. Okay, we can burn both of these things to produce energy. Okay, or to release energy, really, they're not producing it, but to release energy that we can use. So you can have a wood burning stove, use that to heat your house. You could conceivably even use wood to, say, use an engine to power a car. So why don't we use wood instead of gasoline? Like, for instance, wood is a renewable resource. We can grow more trees, right? But we can't make more gasoline because we can't get more fossil fuels. So why would we do that? Well, the reason that we use gasoline is because it's a really high quality source of energy. Okay, it burns relatively clean to some degree. We'll talk about that a little bit later. But clean in the sense of like we get a lot of the energy that we put in, okay, that's bound up in those bonds, gets converted into energy that we can use. Mechanical energy to move the cars, electrical energy if we were using a gasoline-fired generator or something like that. Wood, on the other hand, doesn't work in nearly the same way. It's not very efficient, and it doesn't have very high quality because we lose a lot of the energy transformation goes into the fire, into the heat loss. Now that's good in a sense. I mean, generally when we burn wood, we want some heat. But as far as using it to actually do work, to like say move things mechanically, wood is a very inefficient means. Electricity is a really efficient means, or a really high quality source of energy. But of course the problem is we have to generate the electricity somehow, and usually in the generation of that electricity we lose some of the energy. So we could have a power plant that was entirely fueled by wood, okay, and the electricity at the end would be really high quality energy, but the wood at the beginning was really low quality energy, and so we lost a lot of the energy to heat in the process of making. Okay, now why does all this matter to us in environmental science? Because essentially every ecological process that we're going to talk about all year is the base, the thing underpinning the whole thing are energy conversions. Okay, think of trophic levels. Okay, plants taking energy from the sun, and then we talked about animals are going to eat the plants, bigger animals are going to eat those animals, and at each step of that you lose the vast bulk of the energy. This is the argument, we'll talk about this later in the year, why they would say that, like, as far as energy efficiency, it's much more efficient in that sense overall to the whole globe to be, say, a vegetarian as opposed to being an omnivore like most of us are. Because you lose every stage of the process, you lose a lot of the energy. The energy efficiency says that you don't get 100% of that energy out.